Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my great pleasure to introduce Daniel Kroning. He was I think most of us know him. He did a lot of influential work, the C-bound model checker. He did a lot of work on decision procedures. He's the author of a decision procedure book that's used in many CS departments now. He was a postdoc with David Clark. He moved to Switzerland, and now he's in Oxford. And next week he's going to present an interesting paper about floating point, a decision procedure for floating point numbers. But today he's going to talk about model checking of concurrent systems. Please.
Okay, thank you, Leonardo. At FMCAT. FMCAT, yes. I can begin my presentation on concurrent software by sales talk advertising my presentation, or actually my students' presentation at FMCAT next week's Monday in Austin. Okay. So the sales talk is going to continue, so I'm going to sell you tools to model check concurrent software. Okay. The motivation for this should be clear, and I'm going to be very fast in the introductory part of this presentation because all of you are very motivated about bugs in software in general and bugs in concurrent software in particular. Let me just clarify what form of concurrency I'm after, because there is enough concurrency going around that this term concurrent software is vague and ambiguous enough, okay? So you could, for example, think about programs that communicate via some form of message passing or something like this over a network as being some form of concurrent software. But what I am mostly after is shared variable concurrency, so something you get from, say, using the Windows 32 Thread API, okay? So furthermore, let me clarify that there are two forms of concurrency that I usually consider. So there's synchronous concurrency, which you normally find in very low-level systems, say at the hardware level or maybe in embedded control software. And then there's asynchronous concurrency, which is what you would normally find in what is called concurrent software running on a commodity operating system such as Windows. Okay, and also software that communicates via network is usually necessarily asynchronous because it's just simply difficult to get synchrony over a distributed system. Okay. There is a straightforward way of formalizing this, and it's also worthwhile doing so just very briefly in order to clarify the difference between synchronous and asynchronous concurrency. So in general, we assume that there is a transition relation, and this transition relation would describe the behavior of a particular thread I, and we will write T index I for this transition relation. Okay? We can also partition up the state into the part that is in some sense used by a particular thread, and here in this case we're assuming that there are something like n threads. Okay, the overall transition relation of the system is then simply the conjunction of these individual transition systems in the synchronous case, and in the asynchronous case you will usually see some sort of scheduling decision. This means somebody, say an operating system scheduler, a piece of code, decides which threads gets to execute, and one way to model this is by simply saying exists some choice of the thread I, and then this particular transition relation of this particular thread gets invoked, and this thread makes a transition.
Is there a typo there? So on the left side, Ti is S times Si, but yes. S is the product of S1 to Sn, so it includes Si also, right?
So this is this transition relation. So this is the state where you're coming from. Okay, so the current state, and this is the next state. And the reason why it's S times Si is as follows. When you have a synchronous transition system, you can modify only your part of a state space usually, right?
Okay, I see.
So that's why it's Si, but you can read everything.
Okay.
Okay, so it's not actually a typo. So this is a therefore, your transition relation of your particular thread is S times Si. But since these are conjoined, the entire state space can actually get written in one transition. Okay? And in case of asynchronous concurrency, you would normally assume that a thread can modify everything. Okay? So that's why it's S times S. So if you want, you can also...
you can have private state here also.
You could also have private state here and make it clear by just adding an Si here. And then you would add a constraint here that says that the private state of all the other threads does not change. So that's one way of clarifying this. But I didn't do this because that wouldn't really fit nicely on that slide anymore. And in general, there are systems where a thread can really change its time.
Actually, I have a question. This is a very useful slide for me. On the left side, we have synchronous, right? Clearly, you can model hardware like that.
Oh, yes.
Is there any kind of programming model for software?
Plenty.
Widespread that is.
Yes, there are plenty of programming models in software for this.
Okay.
So there's an interesting cultural artifact here with respect to this. So since I've been doing lots of teaching in all sorts of countries all over the world, I observe the following. So if you talk to an American undergrad or grad student, or and you ask him what concurrency is, they will normally describe something like this: hey, there's a scheduler, and you get some choice of a thread, and that does something, and the other thread waits in the meantime, okay? But if you, on the other hand, grab a French academic or a person who comes from a French academic background, then if you ask them what concurrency is, they will give you this description, okay? And in this sort of environment, these sort of synchronous programming languages are also much more known, okay? And one particular effect of this was the following. So I taught a course on software, on verification in general at Carnegie Mellon University. And it's Carnegie Mellon University, so one homework assignment was model something like an elevator in SMV, okay? And now SMV by nature is this, okay? So it's a synchronous language. We have a clear notion of a transition, and there is no such thing there is really threads, okay? So SMV has processes on top of this, which is just simply simulated by having a thread selector variable, but natively SMV is a synchronous language. And the students were simply not able to deal with a synchronous programming environment. So the idea that two variables change at the same time was completely alien to them. Okay? All right. So for this talk, we're going to focus on this case, and it's important that it's this case.
So the synchronous apart from assembly are things like, is STRL like that?
So yes, so there are languages in this realm of French embedded systems design languages that would fit in this synchronous development framework. Okay, but for whatever reason, they are not that well known in the US, for example, or actually anywhere outside of France. Okay. Yeah, I don't ask me. Okay, so as I said, we're going to focus on asynchronous shared variable concurrency. So no messages being passed, but global variables being written, and this effect is visible to all threads. Okay. So I usually give a bit of a motivational story about this, but I guess here at Microsoft this is not necessary to do that. Okay, so there is a physical argument as to why this makes some sense, and that relates to power consumption in CPU design. So my actual educational background is on hardware, so I did my PhD on processor verification. So that's why I like this entire discussion, and I will be happy with you to discuss low-level details of processors if you want it, but it's not really the point here in this presentation. So one picture I found recently is this. This is doing a very quick job at illustrating this. So this shows the relationship between frequency, which rises when you go here on this axis, and the power consumption, meaning current drawn by the chip when you go up. And so one thing you see here is that this is clearly non-linear, okay? So there's clearly some sort of quadratic relationship here, right? So this means by lowering your frequency just a little bit, you can get very significant savings in power, okay? And so one effect of this is that you can now buy CPUs that have 100 cores, okay? And this particular vendor, Tilera, he actually promises that you can run an operating system on each of one of these. So they are fully featured, more or less. So each one of these has a cache, level 1 cache, and a level 2 cache separately, and they're connected by means of some sort of switch. And they share address space, okay? So another thing which is probably not necessary to point out to any great length here in this audience is that once you have asynchronous concurrency and thread interleavings, and very weird things can happen, and the result your program shows obviously depends on what array you choose, okay? So we have a brief animation here. So if you first execute thread 1, and then the others, you get a particular state in which x is 11 and y ends up being 21. And if you choose some alternative one, then it's obvious trivial, and you can end up in yet another state, okay? So that's, for this audience here, shouldn't be anything of a surprise. So you say in general that your program has arrays, and now, again, a little bit of story about education. So when you talk to hardcore academics, they will tell you, yes, so you should have used locks to make the program race-free, okay? But then obviously any engineer will tell you, oh, but races are great and we must have them, and that's how we get performance, and race-free software is really bad inherently. And a good story that I'm being told there on this question of races in software is by an IBM engineer. And he used as an example an embedded medical device where you have a thread that measures the patient's temperature, computes it, for example, by measuring the length between two signals, okay? And then there's another thread that's responsible for the GUI, and you definitely want these to be two separate threads because the GUI is obviously not important as temperature measurement, okay? And so the idea is that they communicate via some shared variable, and the thread that measures the temperature just writes it, and the thread that displays it just reads it from this shared variable, okay? And obviously, no, you don't care which one you read. Do you read the one of the last measurement or the one of the current measurement? So if they are a microsecond apart, the user who stares at the display will not be able to tell, okay? So the program is full of races, and obviously the result depends in some sense on the schedule, but not in a practical way, okay? So that's why you were happy for the program to have a race. Okay, but the race wouldn't go away even if you put a lock around it. It doesn't make any difference. It's still the same race. Okay, so another thing which I'm going to ignore is obviously the question of low-level memory models. So there's a lot of research on this going on in my group, but I'm not going to cover it in this presentation. So this is Intel assembly, and let me try to make a survey. Who cannot read this here? Okay, so I'm asking who cannot. Okay, who can read this here? Okay, so there are people who are. Okay, fine. So the Boolean property is satisfied. So everybody can read this here. So then you probably also heard already that. So Intel obviously doesn't guarantee you that these move statements are in any sense atomic. And if you start out this program with these cells, memory cells X and Y being initialized with 0, you would sort of hope that you end up with 1 somewhere. But unfortunately, this little piece of code may terminate with all registers EA X and EBX still being 0, which is obviously bad news for us. Okay? Again, a theoretician's answer could be, oh yeah, you just have to add a memory barrier or fence everywhere. And the engineer's answer is going to be that you don't really want this because these fences are horribly expensive. Okay, and so one of the things I'm working on is a tool that would try to identify locations where you really need this, as opposed to locations where you don't really need this.
What's the memory?
Okay, sorry.
What's the memory fence?
A memory fence is simply something that would synchronize the various cores to the point that you can guarantee that they have a consistent view of the memory. So that's a hardware feature that's provided by Intel. Okay. Unfortunately, it's expensive in the sense that it takes a long time to execute, much longer than the actual store operation. So if you have a simplistic point of view that, oh, you're just going to insert a fence after every instruction that potentially modifies shared memory, then your program is going to be 100x slower than before. Yeah, so it's not a very good answer. Okay, so another thing which is likely going to need very little introduction is Boolean programs, given that I'm here. Okay, so I deleted the slides that actually introduce how these are being produced. Is this a fair assumption? That you've heard the Boolean program story before from somebody here? Okay, I see some nodding. Okay, so this new part of the story is here in slide on line 9. Okay, so I'm assuming, since I want to verify programs that make use of shared variable concurrency, but I'm going to deal with concurrent Boolean programs. And this means I need some new statement that will produce a thread. And I just invented a new statement to extend the syntax of these Boolean programs, and I call it start thread. Okay? So it works like a goto in a Boolean program. So it takes a list of program locations as argument, and it, in some sense, branches non-deterministically to all of these. But each one of these branches is going to be done by a new thread. Okay? So this thread inherits the local state from its parent. So all the local variables, say B4, B5, B6, B7 here, get copied before the new thread is spawned off, okay? And they obviously share a view of the global state, okay? These variables b1 to b3 here. And then the semantics is such that the assignment statements that are in the Boolean program are going to be atomic, and there is going to be an asynchronous interleaving between these statements. That's the semantics of Boolean programs, and I trust that I don't need to formalize this here in this audience, and that it would be straightforward to do so, okay?
Can you say again what the difference was between local and global?
So the difference is that the global state is shared between all threads. So all threads see the same values b1, b2, b3. So if one thread modifies, say, b1, this is immediately visible on all the other threads, okay? Whereas if you modify b4, b5, b6, or b7, you only modify your own copy, all right? So technically, you can think of these variables being on some separate piece of memory that's private to each one of these threads.
The thing that's confusing to me is that you do the start thread within the scope of this local declaration. Does that mean that you create additional copies every time?
Yes, every time you do a start thread, you create a copy of these variables. And the value of these variables is guaranteed to be that of your parents at the time you create the thread, okay? But once the thread is created, you can start changing them, and this will not affect the value of these variables in your parent.
Okay.
All right? So this is maybe slightly different from what you would see in a programming language like C, where start thread would only give you a private piece of stack for those things you put on the stack after creating the thread, okay? So I'm not making this distinction here between after you create the thread and before you create the thread. This is not too much of a practical problem because in C you can actually only access variables that are on somewhere deeper in the stack if you had a pointer to it, okay? And these sort of variables would anyway not be modeled with Boolean variables that are in the local scope, okay?
It's an easy way to pass parameters to the thread that is being started.
Oh, yes, that could be used for this if you wanted to, right? To pass some parameters to a thread that you're creating, okay? Again, it's not normally used like this because the way you normally pass parameters to a thread is by giving it a pointer, which points to some designated data structure that contains these parameters. Yeah, and this data structure is normally dynamically allocated. So it happens outside of the scope of these Boolean variables. All right? Yeah? So there's one more extension which is actually not on the slide. So one thing you definitely need is the following. So you need variables with global scope that are thread local. Okay? So you need variables that would be up here. I should probably add this to the slide. Say a variable b1, which is syntactically global, but semantically thread local. Okay, this it's not just specific to Boolean programs, but this has also been recognized by the people who define the ANSI standard and the C++ ISO standard, because the new version of the C++ standard is going to have a keyword thread local, which is going to do exactly that. So I'm also adding this keyword to the Boolean programming language, if you so want. And it has exactly the same meaning as the same keyword in C++.
So the C++ standard,
yes.
Do they enforce that thread local by some kind of a dynamic or static checking?
No, I mean the expectation is that the runtime environment of your system provides that guarantee that this variable that you mark as being thread local is actually going to be thread local.
Oh, I see. So if two threads try to access it, which they
get their own copy.
They will get a copy.
Yes, they get their own. Each one of them sees their own copy. So you can have two threads that write different values into these thread local variables, and they will not see each other's modifications. You're already using this without knowing it. So, for example, in C you have all these global data structures, right? So, for example, local time returns actually a global data structure. Yeah, there are a number of these C IPA calls that have been invented a long time before thread existed, and they made a little hack there to make it appear that you can still use these without interference between threads. Okay.
So your semantics is also going to be that different threads get different copies.
Yes.
Just like
Just like for the local.
Just like
variables.
recursive procedures
Yes.
get different copies of the same variable declaration.
Yes.
Okay.
Right.
That's cool.
So you really need to distinguish local scope from being thread local. So that's why this word local and global here is really dangerous, because it mixes scope and visibility with respect to what the threads do. And one just needs to be more precise when one says local. Okay? Does it mean local scope? Does it mean thread local? And same thing with global. All right? So these are the two things I'm throwing into the mix, which you haven't seen before. So I have a start thread command, and I have this attribute for a variable that makes it thread local, even though it's global scope. Okay? And the use for this is simply to map these existing programming language constructs that existing programs already use into this world. All right? So then the next question that you ask is, okay, where do these Boolean programs, these concurrent Boolean programs come from? And how do we do the usual business of predicate refinement and so on? And the answer is actually that you don't have to do anything. So the box that computes the abstraction needs trivial changes, like you need something that creates the start thread command, okay, and something that keeps track of thread local global scope variables, okay. So just keep a flag for this and then generate the keyword when you need it. So it's a very modest change you need in this abstraction refinement loop. Okay, the good news is that you can essentially use this loop as is in the concurrent setting. Abstraction happens as before with this minor change. Simulation is as before. The only thing to take care of is to use the thread interleaving from your abstract counter example, and refinement also happens as before. Okay, and the only thing where you really need to worry about is how you're going to model check these concurrent Boolean programs. Okay, that's essentially it. So here we have a stupid example of a C program that really needs a lot of context switches before it gets to this violation of this assertion. Okay, so it's clear that here these two threads need to cooperate in order to get there. So to pass this guard, this thread needs to set G to 1, and then to get past that guard, that thread needs to set G to 2, and then to get past this guard, this thread needs to set G to 3. Okay, this is obviously a schedule you would never ever get on a real system because it's just way too unlikely. But at least in theory, yes, there does exist an interleaving that gets you a violation of this assertion. Okay, so this is what the main program could look like. You just have two calls to pthread create, or if you want to think of a Win32 equivalent of this, I probably should make a slide for that. Okay, so this is what the Boolean program for this could look like. Okay, so initially you could maybe start out with a predicate which just says G is equal to 4. And the abstraction for this is also straightforward. Okay, and the only thing that's maybe new is that you have a start thread command here in your main procedure, which corresponds to these pthread create calls. Okay, so you give this to your model checker, and for now assume we have one that model checks these sort of programs. And your model checker is going to do what? It's going to give you a counterexample, and it's likely going to be very trivial, because all it really needs to do is it needs to execute this statement, which it can do right away because it just can run past these non-deterministic guards here, okay, and then just execute this assertion here. Okay, so there's only one thread switch really needed to get a counterexample on this abstraction. All right, so this is how this could look like. So suppose you had a model checker, it gives you a counterexample trace, which begins up here. And whenever you see one of these horizontal lines here, there's a thread switch in the counterexample from your model checker for the abstract model. Okay, so you can see you really only need two switches to get to violate this assertion. Okay, so you can then do your usual simulation, which just means that you collect constraints from the original program in some, if you want, static single assignment form, and you patch these together by means of a big conjunction. Okay, and you give this to, say, Z3. And obviously the problem here is that you will get this back saying, this is not really a trace on the original program. Okay, but the next thing that will happen is you can give this to your refinement procedure, and your refinement procedure will add more predicates until you have all these predicates for all these guards. And in total, you need 4 iterations. You need these 4 predicates, which any refinement heuristics will find for you. It's not really rocket science here. And then you will just get a more elaborate version of this counterexample here that has all these 4 switches that you need. And then your simulation will pass, and you actually do have a counterexample that jumps back and forth between these 2 threads. So this is a demo I like to give to students. Where I actually show them in their programming environment a trace that hops back and forth between these 2 threads and gets to the violated assertion. Okay, So that's not too complicated. And all we really needed for this was a model checker for these concurrent Boolean programs. All right? What I'm going to present from now on is just worrying about that. And the value you get from this is that in some sense predicate abstraction helps you to disentangle some complexity sources here. So we get rid of things like integers or pointers and so on, and we can actually focus on the concurrency aspect of this problem. Okay? And I'm going to become a little bit more formal from this point on. All right? So what I'm going to consider is a composition of n replicated communicating threads. All of them run the same program. Is it clear why I'm running the same program n times? I mean, there's just one program, and even though the threads might have different behavior, they're just maybe executing different pieces of the same program. Right? So that's why it's n replicated copies of the same program, and that's important, okay? So if I had n different programs, the story would be fundamentally different. So it's important that I have n copies of the same program, all right? As I said, so they're shared variables. These can be read and written by all the threads. And there are these local variables, local in the sense of being thread local, not local scope, okay? Where you have one copy per thread, and this is invisible and inaccessible to the other threads, and that's also important. Okay, if you change that, then the entire story again changes. Okay, so this is just to clarify some notation here. The global state is a vector that consists of some part that's shared, S, okay? And then there are n different versions of the local state, L, L1 to Ln, okay? And whenever I'm going to talk about local state, I'm just going to write L index I for the local state of thread I, right? Now there comes another concept which is very important, and that is the concept of a thread state, okay? Now think yourself of being a thread, okay? You always wanted to be a program like Tron, right? Right? So you're a thread. What is it you can see, right? What is it what Tron can see when Tron looks around in his world, okay? Tron can see the shared state and its own local state, okay? You're unable to see the local state of anybody else's. So some pair of S and some Li is what you can see. You as being a thread I, okay? So that's a very important concept here, okay? We now define formally what problem we are trying to solve. So given such a pair SL, does there exist a reachable global state such that L is Li for some I, okay? So does there exist a reachable global configuration such that a particular thread state exists in there? Okay, this is obviously a projection out of this big vector. All right? So at this point, I usually get some comments of the form, hey, isn't this restrictive? And aren't you losing something here in terms of expressibility? The answer is you aren't really. You can do many things. Obviously, any single index properties of threads you can specify this way. Anything that just talks about one thread. But you can also write properties that talk about multiple threads by adding monitors. Okay? For example, if you care to write a mutual exclusion property, which is actually a property about the entire state vector, you can simply rewrite this by adding a monitor which just watches that mutual exclusivity is being preserved. Okay? So whenever you enter the shared section, you would just set the shared variable to true, and when you leave it, you set it to false, and you just write an assertion that says that this shared variable is false whenever you're about to enter it. Okay? This way, you have rewritten the global property into a local one. Okay? Yes, please.
But the predicate abstraction, I mean, the aim is to really analyze real implementation of programs,
right?
Not like textbook algorithms. And
yes.
Therefore, I mean, when do you really have a situation, a realistic situation, where all the processes, all the threads are identical?
Well, the trick is simply as follows, right? So in a real algorithmic setting, you could, for example, have a situation in which you argue that you have a device driver, and that's really one program, but there are multiple instances running of it. Okay?
So are you going to talk about, or do you envision an abstraction scheme, for instance, that could take processes, threads that are different, yes, but abstract them in such a way that they would match?
Oh yeah, that's actually very easy.
That
yes.
Assumption there, but the one that
right
in your previous slide.
Yes.
Because it doesn't handle even the example that you had earlier in the talk, right?
Right.
So, so that's a key, really.
Right. No. So this is actually that is actually very easy to achieve. All you need to do is the following. So you could, for example, use local state in order to make the thread that you start distinguish what it's doing. Okay. Another thing to realize here is that the start thread command can actually be used in multiple locations. So there can be more than one. Okay. This means you can actually for each thread that you create, you could have a separate start thread command that jumps to a different control location. So the usual scenario in which you have, say, different procedures for each one of the threads fits very well in here. All right. So, and that's simulatable with this model of computation without any effort at all.
But it will complicate, of course, the matching counterexample that you can get to real.
No. You get exactly the sequence of control flow locations that you expect to get. Yeah, so this is not complicated at all.
But I saw that you just say that, imagine I have two threads that start in different states.
Yes.
You can abstract them in a non-deterministic fashion and have them both start in either of those.
No, you can make this deterministic.
And therefore it matches your framework.
I will show you how to make this deterministic. So one thing you can do is, one thing you actually exploit here is the fact that it's asynchronous concurrency. It's a subtle point, but it's important that the concurrency is asynchronous. If you use this in a synchronous setting, it wouldn't work anymore. Okay? So you know something about the initial state, say that all the variables are 0 or something like this. Then a thread starts executing, and this thread will then try to find out what it's supposed to be doing. Okay? And it just simply looks at the global state and say, counts up a counter, which you can build with Boolean variables if you want. Let's say a unary encoding. Okay? Then it decides I'm thread 0, so I'm going to run procedure A. Okay? And then the next thread that starts running sees that the counter is already at 1 and says, okay, I'm supposed to be executing procedure B. Okay? So even though all of these programs, all of these threads start out executing the same piece of code, they can in fact deterministically execute separate procedures. Okay? And all you've added is one statement at the very beginning of your program. So you're really not losing anything by saying that these are identical procedures that are being executed by all threads. It's not a restriction at all. It doesn't cause any encoding complexity, or the counterexamples aren't getting any more complicated or anything of that sort. Yeah? So it's a no-pain translation. Okay? And in fact, we actually do it in the model checker for the Boolean program itself. So the counterexample that comes out of the model checker looks exactly the way you expect it to look like. All right? Actually, I'm going to iterate on this point. Since all these replicated threads execute the same program, okay, one thing you will notice is a lot of redundancy in the states that you explore on this. Okay, remember we also have shared and local state space, right? Which is this S here for the shared space, and then I use these uppercase letters A and B for states over these local variables. All right. So now, one thing to remember is all the variables are Boolean. Okay, so this means there's no such thing as a thread ID that can float around there. We only have Boolean variables. Okay, and that in particular means that it's actually irrelevant what thread number a thread is. Okay, so you can't really distinguish thread 1 from thread 2. There's no way they can tell which one they are. Okay, so in particular, if you think about the case of 4 threads, and suppose you have 2 threads in state A and 2 threads in state B, okay, then you could just as well say that there's the same state in which you first have the B's and then the A's, or first a B and then 2 A's and then a B, okay? All of these, from point of view of the semantics and behavior of the system, are completely indistinguishable. And you can actually prove this. You can make a formal argument that if you reorder these threads at any time during your exploration, you will get exactly the same set of regional states at the end. Okay? It causes no loss of information at all to shuffle these threads around. It's not an over-approximation. That's important. Okay? So, which means this model exhibits some kind of specific symmetry here. Okay? Yeah.
Come back to this point, but if I may.
Right.
So it sounded like you just said in a minute that you can make basically non-symmetric systems symmetric.
Right.
By either using non-determinant or using some deterministic behavior where each thread individually will be able to access read this counter that tells how many threads are in that state, etc.
Yes.
But that breaks the symmetry.
No, it doesn't.
But if you have two threads, the
Yes.
first one sees the counter and there's, oh, nobody has a start like
Yes.
this procedure here, and the second sees it.
Yes.
You have.
Yes,
you don't
but
have
you can still at any point in time swap the two without having lost anything. The only thing that's relevant is how many are in that particular state, but not which one is the first and which one is the second. Okay?
Along the same lines, if you think sometimes programs do use the thread identifier
Right.
to do some unique things,
Yes.
but in that case it's just part of the state. So I mean his story holds up. It just means that the states would not be the same.
But you have like A and B communicating, and then you define A plus B, parallel A plus B, and then you gain some symmetry, but you have a much bigger state space at the end. So because you have now both, so I don't know, but I'll let you go on.
Right. So the claim I want you to believe at this point is that I can shuffle my state vector arbitrarily, and I'm not losing information, and then I'm not adding behavior. So that's something you would believe at this point.
Yes.
Okay? I just sort these.
Fair enough, fair enough.
Okay? Not an over-approximation, not an under-approximation, and that's because there is no such thing as a thread number that you can access. Okay? Right? So the idea is therefore fairly straightforward, what we're going to do, and that's something called counter abstraction. Okay? And it's a bit dangerous to use this term because this term has been used for many different things. So this is a little bibliography of ideas that have been floating around in order to do this sort of symmetry reduction. And this term counter abstraction comes from this paper here, so the P, I believe, is Pinoeli. And they use a very specific kind of counter abstraction in which they truncate counters once they exceed the value of 1. So they distinguish the case in which there are 0 threads in a particular state, 1 thread in a particular state, or arbitrarily many threads in a particular state. Okay? And that's obviously an over-approximation. As soon as you say you don't really track how many threads are in a particular state, then you lose information. Because it's maybe important that there are only 2. Okay? So the key thing here is we are not doing that. We are keeping these counters precisely as they are. We never lose any information about them. Okay? No over-approximation, no under-approximation. This is precise technique. Yeah?
What about programs that can dynamically spawn an unknown number of threads?
That's going to be the second part of the talk. Would it be acceptable for you if I postpone the question?
I mean, so the current assumption then is that
The current assumption is that there's some number n, say 4 in this slides. Okay? But there's going to be a second part of this talk where I'm asking what if n was unbounded, right? So for now, what I'm assuming is that I can represent my set of states as follows. I will just keep track of some shared state, and then I'm counting how many threads are in a particular local state. Okay, these counters are never truncated or anything of that sort. So what I'm claiming is that up to this symmetric permutation, this is producing the exact same set of states. All right? Yeah. So now this is all nice, but it's all something you can at least argue is anticipated by the literature. Now there's our contribution, and there are 2 things here. These are all very technical, so it's not a new theoretical idea. It's a low-level programming implementation type of idea. Okay? So let me start with the obvious one. So when you have these sort of vectors here, and you count how many threads are in a local state. Okay? So essentially what you do is, for every conceivable local state, you keep a counter. So one technical contribution we made is that we say, okay, we observe that there may be many local states. If you think about a Boolean program, there are 2 to the power of k local states, where k is the number of local variables. That's a lot. Okay, so if you have 50 predicates, you have 2 to the power of 50 local states, actually times the number of program locations, because the program counter is also part of a local state. So there's just way too many. So one easy observation you can make is that if there are n threads, then there are at most n of these counters that are non-zero. Okay, so if I have 4 threads, this means at most 4 counters have a non-zero value. But if I have a billion counters, possibly, this means pretty much all of them are going to be 0. Okay? So one obvious optimization you can make is that you omit all of these 0 value counters from your state representation. And this gets the complexity of these procedures down from n to the power of l, where l is the size of the local state space, to the minimum of n and L, okay? And the thing here is that the number of threads n is typically much smaller than the size of a local state space. Yes, please.
Is that what amounts to delta encoding?
I'm not sure if it's really that.
But is it?
It's some form of encoding, yes. So you omit.
You say how many you have. In principle, you have all locations available, and then you say how many locations you skip until the next one.
Yes. So think of a matrix, and you just want to represent the non-zero values because it's very sparse. Okay, that's the idea. Okay, so it's not a terribly deep idea, but interestingly, if you look at the existing tools, all of them will expect input where you explicitly list all the local states in a file, right? And they explicitly build the set of local states. So there's nothing where you could, there's no existing tool where you could just go ahead and translate a Boolean program into because the translation is already exponential. All right? Yeah? So you need to get rid of this. You only want to store, create, and talk about local states that are in some sense in use. And obviously you need to do this on the fly without actually translating a Boolean program into that. Because you don't know up front what local states are going to be reachable at what point. All right? So another little trick is, and that's actually related to this, is obviously you need to put these counters in the context of a particular instruction. All right? Because when you look at a particular piece of code in your Boolean program, you actually really know exactly what it's doing, and you can tell which counters are possibly modified. All right? So as opposed to drawing something which is called a global state transition diagram, which you will find in the literature, where they tell you for any conceivable possible state what your modifications of these counter values are going to be. Okay? So the two things you need to do is get rid of the zero value counters and store separate state sets for each program location. That's something that any explicit state model checker would certainly do, and any symbolic model checker would likely do as well, that you would have separate symbolic representations for the state for each program location. And that's something you will not find in the literature here. Okay? All of these assume that there is some global state transition graph. Okay? So the savings are obvious, so this slide illustrates this, right? So if I have a vector like this with all of these zeros, you can think of what happens when you make a transition. Say you change A to C, okay? When the value from the counter for A gets decreased and the counter for C gets increased. And what you do instead is the following. So you start out with a vector where it only contains a counter for A, a counter for B. A goes away because it becomes 0. You kick it out of your state vector. And C goes in, okay? Actually, I think this arrow here should point in the upward direction. Should point up, goes up, okay? That's essentially what you need. So it requires some bookkeeping because the position no longer tells you what you're counting, so you need to remember what these individual positions in your state vector are. Okay, that's just some bookkeeping, okay? So there are a number of problems that arise in this. And again, this is a fairly low-level implementation issue in some sense, okay? So what essentially we have is the following. So we have a representation that is a cross product of some local state, and then, some shared state, and then some number of local states and a counter value. Okay, that's what we are storing, all right? And we're going to use a symbolic representation for this. The reason why we use a symbolic representation for this is because Boolean programs have a lot of non-determinism. And you're not going to get this non-determinism away. It's actually important because of the abstraction in order to be sound. Okay, so this is going to stay, and you need to handle it. And the only way to handle this non-determinism is by means of some symbolic representation. Okay, so now what kind of symbolic representation can we actually use in this context? So what we experimenting with is to have separate BDDs for each one of these. So we have a BDD that represents the shared state, all right? And we have separate BDDs for each one of these local components.
But then how do you get correlations?
Oh yeah, that's exactly what this slide is about, okay? So how do you encode correlations? So before we get into how we do the correlations, let me first discuss the alternative option, which is to have one huge BDD for everything, all right? In which it's very easy to capture a connection between this and, say, that, okay? Okay, yeah, it's not good enough because the BDDs get very large and ugly. Okay, BDDs is a bit of magic. right? And a good BDD is a BDD that talks about few things, all right? And so this was actually an implementation we had tried. So we had implemented all this story with a global BDD. Okay, I will tell you why it's not really working out. First of all, it's a BDD that talks about a lot of variables. That's always bad. And second, remember that we need to keep these state vectors canonical, okay? And that in particular means that we need to come up with some ordering of these. Okay? So A always has to be before B, and B has to be before C. If we start having an arbitrary ordering of these, then these vectors are no longer canonical. All right? When the same set can be represented by two different data structures. And that will make my fixed mode detection really hard and all sorts of other bad things. And so what I would have to do in this scenario is I would need to rename these in the order of these local states. But remember, these local states are represented by a BDD. Okay? And so I would need to compare BDDs, sub-BDDs inside a bigger BDD, and according to this, need to shuffle it around. And that means I need to reorder the BDD's variables in order to shuffle these around. And that the complexity of that operation depends on the distance inside the BDD vector. And that's unfortunately a very expensive and complex operation, and one that doesn't work well at all. Yeah? So it turned out that this was an approach with a lot of pain. It took us a year to figure it out. With a lot of pain, we figured out that this global BDD that represents a shared space, the local states, all in one BDD, that didn't work out for us. We put a lot of work in trying to research better ways of changing variable orderings and so on, and it never worked very well. Okay? So that's why we ended up with having separate BDDs for all of these, which has the advantage that these separate BDDs are small because they only talk about few variables. Ordering them is very easy because BDDs can easily be compared. It's a very inexpensive operation. And if we were to swap them around, it's also inexpensive because it's a constant time operation to swap around if they are separate BDDs. If it's one BDD, it's really, really, really expensive. And now it's constant time. Okay? Right, so the question that remains is, what if I have a statement that establishes some sort of connection between, say, a shared variable and a local variable? But you could have the same question about what happens if I have a connection between two threads in some sense, that they agree on some variable or something like this. Okay, how do we do this? Right, if it's a separate BDD, there isn't really any way to express this unless these are constants. Right, so I can say here that x is true, and I can say here that some local variable is true when they agree on it. But if I want to say it's either one of true or false, but the same in both, then there isn't really any way of doing this. Right? Is that clear? Yeah? So here we have an example for this. So this is a state vector. So we have two threads in which some local variable is 0. And suppose we don't know anything about the value of this global variable here. Yeah? And then suppose I assign the global variable to be L. So that's not problematic at all, because here I'm copying a constant. So this global variable or shared variable just becomes 0, and the local variable just stays 0. Okay, this is just fine, this scenario. Okay, this is no problem at all. But what if the local variable wasn't defined before? Okay, so it's a non-deterministically chosen value. So this can represent any value here. Sorry, column 2 just means, remember up here, we have a local state, and this is a counter value. This means there are two threads in this state. Okay? All right? And by the way, so this means there are two threads that agree on that value. Yeah? All right? So if I did this, so if I just copy the star over, that's obviously wrong, right? Because then that just means that they are really the cross product of all these threads.
What does a local state L is equal to star mean?
But it's either 0 or 1, right?
But
it's not initialized.
It's not initialized, or it comes out of a non-deterministic choice.
The way I'm reading it is that for each state, there's the number of threads there, right? So L is equal to star colon 2 means what?
It means that
so there are two threads at L is equal to 0 and two threads at L is equal to 1.
Yes, but they agree. So it's the same state, but you're not saying whether it's 0 or 1. But both of these threads are in the same state. So this represents really, how many, oh yeah, good question, how many states does this really represent here?
Yeah, okay. So
Altogether, this represents 4 states, right? Because you have a choice for the global variable, and we have a choice for this local variable, all right? And the fact that there are 2 of them just doesn't increase it, just means the vector is a bit wider, okay? All right? So the point is I can no longer just copy it over, because if I just copy over with star, it doesn't actually change the vector. But it should, because now there is a connection between these variables, and that needs to be represented somehow. All right? So what I unfortunately need to do in this case is I need to split. All right? So this means I need to make a commitment as to these 2 cases of L being 0 or L being 1. I need to branch up this non-deterministic choice at this point. And then it's clear how to do this, right? So I just do these 2 cases separately, and I just told you that if it's a constant, it's no problem at all. All right, so I just split it up, and then I get these 2 cases in which S is 0 and S is 1, and the corresponding local variable has the same value. All right? So that's no problem at all, once I split it up. All right? Sorry.
So the column 2 is number of threads?
The number of threads in that particular local state, yes.
So there are 2 threads
Yes.
that's where the local variable can be anything.
Yes.
But they have to be the same,
Exactly.
even if they're
Yes.
in that notation.
Right.
So now I can think of your representation earlier was a conjunction of local BDDs.
Yes.
Now it's a disjunction of such conjunctions.
Yes.
When you split
Yes, so
it
I need a
up,
list
it's
of these. A disjunction of conjunction of BDDs. That's
Okay.
right. Yes, exactly.
So do you split whenever you have something on the
All right. I'm
right-hand
gonna get to exactly the condition in which I split.
So before that,
Yes.
so can any set of states be represented as a disjunction of conjunction of local BDDs?
Yes. In the worst case, you enumerate.
So this is you're jumping from symbolic encoding to much more explicit here. When you
Yes. So it's a bit of a hybrid.
Oh,
Yeah,
I see.
exactly.
So in
Yeah,
the worst case,
explicit on
we
top.
just go to the enumerative
Yes,
representation.
yes.
That's allowed here because
Yes.
that'll be like a full disjunction.
Yes. Yes.
Okay. I see.
Yeah. So one thing that I didn't mention, I'm not going to mention it again, was just to want to point it out. There's also opportunities for merging again. Okay, so I'm not just let this disjunction grow, but at some point I might also realize, hey, I can throw these 2 things together. And there are some conditions for doing so. Okay? And you need to be careful to remain canonical when you do these sort of things and not over-approximate. It's very easy to mistakenly over-approximate
So
when you
the
do these
moment you
mergers.
split, you also lost your canonicity.
No, so because you just keep this list of disjuncts and you can just do a pairwise comparison. So it just gets a bit more expensive to do a fixed point detection, but it's still canonical. Okay? Just slightly more complex. All right? So there's a formalization of this property, and we call this situation in which you have communication between a local and a global variable a splice state. All right? And this is simply the formal definition of what a splice state is. And they always result from communication between threads. Okay? You can always use this as a definition of what communication between threads is, that they create splice states. And something that doesn't create a splice state isn't communication. All right? So the kind of syntactically, you can tell which kind of statements can produce this. So there needs to be some communication between some local and some global variable. All right? And whenever you execute these, you just simply do a Shannon expansion and split up. All right? And now, one question that's obvious to be asked here is, aren't you going to be punished for this? Because there's obviously potential for exponential growth here. All right? And the answer is as follows. So this works because on real-world Boolean programs, there are relatively few of these splice statements. Only 12% of the statements we found in real-world Boolean programs can syntactically generate a splice. So the others are unable to produce a splice state syntactically already. Okay? And furthermore, so one thing you will notice here that this is worst-case exponential in the number of variables that are involved in this splice state. But in practice, there are very few splice variables in these few splice statements. So in practice, it's usually just 1, only in very few cases 2. All right? So that means that this is contained. And only very few real-world states that are reachable, so it depends on what states are reachable, actually require a duplication of your state vector, only 10%. All right? So 12% of the instructions can potentially splice, and of these only 10% do. So it's really about a percent of the instruction that is doing the communication and where you actually need to do splitting, right? And as I said, there's the opportunity to merge back again, right? So one thing which is critical in practice here is to keep the program counter separate in these state vectors, because obviously otherwise everything would be a splice statement if you merge it all into one huge magic monster statement, all right?
So the program counter is a part of the local.
Yes, exactly. It's part of the local
Is
state.
that encoded in the BDD for the
No, it's not encoded in the BDD. It's kept separately.
Oh, so you have that explicit too.
Yes, we have that explicit too.
Explicit, you have
Yes.
your program state, you have
Right.
the BDD,
Yes.
and under that.
Yes.
Okay.
All right. That's something very common, actually. I mean, most model checkers for software work this way. Okay. So let me get to experimental evidence why this is useful. Okay. So we ran this on any Boolean program we could get our hands on, and I have a student who got a job assignment to nag anybody he knows and ever talked about Boolean programs for more Boolean programs. Okay. So we have.
Where do you find so many concurrent Boolean programs? I can believe that there are a few Boolean programs out there, but what about concurrent Boolean programs?
So we did the following. So we nagged Byron, and we constructed some from SLAM benchmarks with some effort to identify what is initialization and what is actually code that's supposed to run in concurrently. And we made a harness that specifically creates threads for Linux device servers. So essentially it's meant to mimic what SLAM does for Windows device server in the case of Linux device servers. And there is great care taken to actually separate initialization routines from the actual code, and then again at the end clean up code. Okay, so that we carefully separate out what is meant to run concurrently from what is meant to run sequentially.
So how many different dispatch routines are you running at the same time?
Well, I'm going to get to this.
Okay.
Right. So what you see actually here. So this answers your question to some extent. Okay.
And just to follow up on that,
Right.
so there is communication between these different.
Oh yeah, sure. They communicate. If not, then the whole thing is very trivial.
Yes, but I'm just checking.
Right. Sorry. No. Very. Yeah. I mean, we send 12% of slice license need to come from somewhere, right? So if I have disjoint, if I only have local variables, then that value would be 0. Okay. So so this is a scatter plot, and normally in scatter plots you have like dots or crosses, but here you have numbers. Okay. So if you don't see them, you can just come a little bit closer, and you see that there are lots of little numbers here on this scatter plot. All right. So the number is actually the number of threads or the number of dispatch routines that's operating. Okay. So you see lots of little 2s, some 4s, 5s, and some 7s, 8s. Okay. And there's a big.
Actually, I have one more question.
Black bar here. Okay. Sorry. Yeah.
Did you model only concurrently running dispatch routines, or did you also model asynchronously generated completion routines or cancellation, or DPCs, ISRs, those kinds of things?
There's also in the case of the Linux routines where we had some more expertise on what is going on, we also had an interrupt service handler,
Okay.
and we also had the equivalent of what Linux would, I guess, call cancellation. Yeah, so there's also a cleanup routine that tries to wait for threads that run, and so then you remove a module.
I see. So
Okay.
in these examples, you actually did have control-dependent creation of threads.
Oh yes, definitely.
I see.
Yes. All right. Okay, back to this scatter plot. All right. So these little numbers denote the number of threads running. Okay. And so this is comparing our symbolic model checker with this counter abstraction against a plain symbolic exploration without this abstraction. Okay. And so whenever the number is above this diagonal, then this means our algorithm wins, and whenever it's below, then the traditional method wins. Okay, so it's easy to see that the vast majority of numbers is above the line. And another thing you will see if you go really, really close to the screen is that above the line you only find 2s. Okay, yes, please.
So for the plain symbolic exploration, what BDD encoding did you use? One after the other, or interleaved? Would it be interesting to
It was interleaved.
interleaved?
Yeah.
That's good, because that's probably the most promising.
Yeah, so we put a lot of work in trying to find out BDD variable orders and all these things.
I don't know if there was this work in the 90s
Yes.
about partition, BDD-based symbolic model checking
Yes.
with partition transition relations.
Yes.
by Macmillan, Birch, and David Long, etc. So that's why because they also
so we also use a fairly sophisticated BDD library that tries to do a dynamic reordering and all these sort of things. So we put some amount of work into getting our comparison work. So one data point I can also contribute is that for the sequential case of having just one thread, its performance is very much comparable with that of Bebop. Okay, so it's not completely crap. That's what I'm trying to say. No, I mean, there's a lot of magic in BDDs, and it's I completely agree. There's a lot of magic in BDDs, and since we created the comparison point, it's fair to ask, the thing you're comparing with is that maybe it's just plain dumb, right? So what I'm trying to claim is that the comparison point is not plain dumb because we put a lot of work into optimizing it, and it compares well with other implementations at this level.
You're saying that the thing that is below the line, if instantiated on a thing with single thread is competitive with Bebop. That's why it's a good comparison point. I understand.
Right.
That's very good.
So another thing we compared against is SMV. And it also compares favorable with that, but that's a bit unfair because SMV is obviously not optimized for this case, right? But it means it's not completely dumb, right? And another thing we did is we also made an explicit state version of this, which I unfortunately didn't bring the slide for, and compared that against Murphy. Okay, so Murphy was hand optimized by somebody who really knows about symmetry reduction and these sort of things. Okay, so obviously Murphy isn't able to deal with data non-determinism. But if you take Boolean programs with reduced data non-determinism, then you can make a fair comparison of Murphy against a version of this algorithm that's explicit state. All right, and our algorithm also compares favorably against Murphy in this setting. Yeah, obviously we're not comparing the symbolic version against Murphy. That would be again unfair. But we're comparing an explicit state version of our algorithm against Murphy. Okay. All right, so let me point out some more properties of this graph here. So one thing you will notice is that the very high numbers tend to be very much in this corner. So the higher the number of threads, the more we gain. All right, and in particular, you will see that these are actually very much here. This means you actually see sequences of numbers that are staying on this side, and you increase the thread count, and you hardly pay any price in terms of extra computational time. Right? And this is in some sense intuitively right because this whole counter abstraction just lives from merging identical threads. And if there are only two threads around, then the best you can always get is that there's one thread counter that has the value 2. Okay, that's the best you can hope for. So there's not much potential for a reduction. But if there are 8 threads around, then obviously there's much more potential for being in the same local state, and you can save much more. All right, so that's why this is not actually very surprising. But the higher the thread count gets, the better our algorithm compares against the alternatives. All right? So one thing which is also important is that there's this huge blob of black here, which is all numbers. And actually a very vast majority of these programs, for any thread count that's not 2s, is really only solvable with our counter abstraction. And it's not solvable with a plain symbolic exploration. So it's really enabling. It makes a big difference in terms of the number of benchmarks you get through in some timeout. Okay? All right. So this is, by the way, up to this point, this is what was presented at CAV this year. And I'm now going to switch to a part which wasn't yet presented at CAV. Okay? So, oh yeah, before I get to this, here's the URL if you want to download this and try this yourself. So this has a BSD license. So it's not GPL, so Microsoft employees are very much authorized so there's no legal constraint that would prevent you from trying out this code, okay? Let me just mention that. So, now I want to get to his question, all right? So doing this for some number of threads is fine, but what we really, really want is the case in which where you have some loop that can spawn threads dynamically at will, right? And you don't want to commit a priori what kind of number of threads it would be, all right? And so remember that we had this case of, and now it actually really becomes important, that we have a case of a program with replicated threads executing the same Boolean program, all right? So we have this model M that's parameterized in some number n. N so far was a constant, And now I want n to be a variable. All right? So this is called the parameterized system verification problem. This has been around for many years, okay? And there's a paper, this is a paper that shows that this is in general undecidable. And the proof is actually fairly easy, so.
I should go back, I'm kind of confused
Yes.
about this undecidability result.
Yes.
So, I would imagine that I would not formulate the problem like this.
All right, I'm going to get to this. I think I can anticipate your question. So the thing is that obviously, if you take an arbitrary family of these sort of models and a property P, then this is a slightly more general problem than the problem of having Boolean programs with n threads.
With arbitrary number of threads.
With arbitrary number of threads.
What's going on is that there are some assertions floating around, and
Right.
you just want to check if some assertion
Yeah.
fails. Doesn't matter
Right.
how
So-
long you run the program.
I'm going to get to this. So the point I'm trying to make is that there is this well-known claim that in general the parameterized verification problem is undecidable, but for this specific case of Boolean programs, it actually is decidable. Okay? So I just wanted to clarify this, that I'm obviously aware of these results showing that this is undecidable, and I'm also aware of the fact that this is a special case, and therefore this doesn't apply. All right? Yeah? So Boolean programs without recursion with unbounded number of threads are not Turing complete. Right? So a relatively easy way to see this, so it again depends on the community you talk to. For example, we talked to people at NEC, and they were surprised by this. So they were thinking, oh, this has to be undecidable. But then if you talk to people in the Patrinet community, oh yeah, it's triviality, right? So it's coverability. Yeah, so it really depends on what community a person comes from. So in Germany, for example, where Patrinets are huge, everybody knows this, okay? But here in the US, don't seem to be that many people who have seen this before. Okay? So you can sometimes surprise people. Like I do this. So I like having little surveys in my lectures. So I show the students some problem, like I tell them, blah, 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 what have you seen so far? And then ask them, and then what if I make this number of threads unbounded? Is this still decidable? And try to make a majority vote thing as to who thinks whether this is decidable or not. And usually there's a clear majority for this being undecidable. All right? So no matter where I try this. Okay, so the argument why this is decidable is that you can rewrite Boolean programs into vector addition systems, and there is a fairly ancient result that explains that coverability in there is decidable. And the argument is well, where do I have it? That you can use a procedure called the Karp-Miller tree to produce a conservative tree of states that the system could be in, okay? And the only thing you then need to see is as to why a Boolean program is really expressible as a vector addition system. And to see that, I'm going to illustrate what a vector addition system is. So in a vector addition system, you have states. So we have 3 states here. That's meant to be an initial state. That's why it's labeled with I. And there are 2 states here which are used to distinguish the value of some shared variable. And together with these states, you have vectors of integers. These integers are potentially unbounded, all right? And they can be manipulated by means of adding or subtracting these constant numbers to them, okay? So this means increase the first counter, okay? And this means don't change it. This means decrease the first one, increase the second, okay? And this means decrease the second, increase the third, okay? So these are not as expressive as counter machines, for which you would already have undecidability for 2 counters, because you can't really compare. So you can't do relational operations on these counters, all right? So the question is, how do we actually get a vector addition system from one of these Boolean programs? So the trick here is, again, essentially the same idea we did before to get the symmetry reduction. So we count how many local states there are. And we use these counters in the vector addition system in order to keep track of this, right? So for example, if we were to make a transition, if we were to execute the statement here, number 1, in which we set variable s to true, and suppose we come from a state in which it's false, we simply need to increase the appropriate counter for that particular local state, all right? So actually, this vector addition system down here is meant to present this little Boolean program here, all right? And I actually did have a master's student whose job was to take a Boolean program and translate it exactly into this form. Okay? So one catch that you have here, obviously, is the following. You run again into the same problem that we had before, namely that you actually need to have one of these entries in your vector for every conceivable local state. And remember, the number of local states is exponential of the number of local variables in your Boolean program, and this means there are too many. All right? So our contribution here is, again, similar to what you've seen before. You don't even ever build the vector addition system explicitly, but you, in some sense, need to intermingle the exploration of your state space with the construction of a vector addition system itself. And the trick is, again, to not even ever store zero counters. And you can do the same trick for the case of a vector addition system. All right? Another problem that pops up here is that if you look at this original construction by Karp-Miller, is that it has a non-primitive recursive space complexity, which is a really bad news. There exists improvement that you can find in the literature that makes this X space complete, but it's still pretty bad. All right? Really bad news. I mean, normally we deal just with P space complete things. Okay? So we still have implemented this. All right? And with a number of optimizations, such as not storing the zero counters and so on. And this is what you get. So this is this axis is benchmarks, okay, sorted by the time it takes to compute the set of states reachable with an unbounded number of threads. And this is runtime in seconds, okay? So this is 1 second here. So you can see the vast majority of these is solvable within 1 second. And this is for an unbounded number of threads, all right? Obviously, this problem of complexity hits us at some point. So there exists some number of benchmarks which are simply too hard for us right now with this procedure, all right? But it's a fairly small number of these.
So how are you creating these unbounded number of threads?
You simply have a loop, and that loop contains a start thread command.
And so do you get these from the device drivers also?
Yes.
The same thing, infinite number of dispatch routines.
In fact, this is the same set of benchmarks for both problems, only that in the first case with a bounded number of threads, we simply stop creating threads after some time, after some number of threads have been created. Okay?
So these were the same benchmarks?
These are the same benchmarks, yes.
So because before you didn't present the absolute numbers for the comparison with regular symbolic execution.
Oh, no, this scatter plot shows absolute numbers.
Maybe I missed that.
That's seconds.
Okay,
so this is the 1 second. So what you can see is that the Karp-Miller is actually faster in many cases. So we computed the place where they have the same speed. Like how many threads do you need for the bounded case to get the same time, runtime, roughly the same runtime as the Karp-Miller procedure. And we observe that in many cases that number is something like 1 or 2. Meaning in many cases it's actually the case that exploring the set of reachable states for an unbounded number of threads is exactly as expensive as exploring the set of reachable threads for 1 thread, okay? Right? So as I said, there are cases that are too hard for this, yeah? It's not the final answer to this, but for many real-world programs, you get a very inexpensive answer as to what the set of reachable thread states is for an unbounded number of threads, all right? Okay, so let me conclude. This works for arbitrarily many threads. No more question about whether you just need 1 more thread to get the bug, okay? This does handle dynamic thread creation. Yeah, control flow dependent if you want, okay? Is precise, so this is not an over-approximation. It's not an under-approximation, all right? What is missing is recursion. But at least for our experience that with device drivers, there is usually no interesting recursion happening. All right? Thank you. Question, yes?
So I'm still trying to understand like what kind of concurrent programs you're covering. You said it's drivers mostly.
Right.
So one thing I could imagine where this has problems is in parallel computations, say you have an 8-way barrier between 8 threads. It seems immediately that you would need to model the counter to have, precise number.
Barrier is something very special. I strongly suspect that you could come up with something in this setup that would implement the barrier without using a counter.
Okay.
right? So you essentially would not consider.
I didn't understand your question. Why is that a problem?
So in the barrier you have like threads, 8 threads do something concurrently, and then they all synchronize by waiting for each other. So you would have some count that counts how many have reached.
Yeah. So the normal way of implementing a barrier is that you're aware of how many threads there are.
Then there will be some global variable, right?
This would be some global variable, and it would obviously depend on the number of threads that are running, which doesn't really fit this model, because there's no way here to find out how many threads there are.
Oh, you're talking specifically about the infinite thread case.
It's also a problem for the finite thread
parallel
case.
programs that will launch exactly 8 threads and will initialize the counter to have the number 8 in it, and then we'll wait for those 8 threads to.
Yeah. So what my answer to this is that likely what you want here is the equivalence of a barrier in a Boolean program. But you are able to do this while you explore, because then it becomes actually fairly easy, right? You just simply don't consider transitions that cross the barrier while there are still threads that are not yet at the barrier, because that's a control flow property. It's not really data, okay?
I think, yeah, so if you encode the barrier somehow directly instead of taking...
It had a very similar observation. So if you push the concept of a lock down into a Boolean program, you can get much better precision as opposed to trying to model it with Boolean variables and so on. Yeah. One reason is, one simple observation that there is because there doesn't exist a shared state in which you have 2 threads that have a lock. Right? So this is something you know you can rule out and you don't ever need to consider. Yeah? So meaning there's probably some case for having some of these concurrency primitives like barriers or locks down at the level of Boolean programs as opposed to trying to replicate them with Boolean variables. Like the case of a counter to get the barrier is certainly a strong argument. I mean, you would have to emulate this with some stupid Boolean variables, and it will certainly cost you.
So this is very good, actually.
Why?
How come you have not done that already?
To have a barrier in there?
I mean, to have all these synchronization.
I have locks
in the
yeah, which should probably be done. So one should probably do some thinking as to what the most needed concurrency primitives are and add them to Boolean programs. Because handling these in the model checker during exploration is fairly inexpensive. I mean, it causes some implementation work, but it doesn't add any complexity. All right? Yeah. But encoding these as Boolean variables is likely going to be pricey. All right? So that's my answer to this. Right. If you put it into Boolean variables, it's likely not going to work very well. But if you put it into the Boolean program as a specific primitive, then I don't see any reason why it shouldn't work.
Right. That makes sense.
Mm-hmm.
Cool.
All right. Yep.
Okay, so I mean, I'm still struggling with this, the applicability basically, and I mean, in my mind, and I don't know if you agree with that, but the reason why symmetry reduction hasn't had that big impact in model checking, it's because it's very rare. It's very hard to find really symmetric systems. I mean, and so now one key question is that through abstraction, can you have more symmetric systems?
Oh yes, that's definitely the case. Yes.
And the second thing is like you mentioned Murphy. So Murphy is probably arguably perhaps one tool that leverages the most basically and has the most compelling application domain for this symmetry reduction, which was this cache coherence protocol.
Right.
And you have lots of symmetries due to data symmetry actually.
Right.
So now in Boolean programs themselves, there's no data symmetry, but now you could also think of other type of perhaps more richer, more precise abstraction, where you still capture these symmetries and be able to take advantage of these type of techniques, etc. I don't know if you agree with my overall assessment first that about like roughly so far the impact of about symmetry reduction, and second, I mean, have you thought more about how abstractions, I mean, the interaction between symmetry and abstraction?
All right, okay, let me begin with the first point, the interaction between symmetry and abstraction. I mean, there's obviously a case here. By the fact that we produce a predicate abstraction, there's certainly many more symmetries in the abstract model than you find in the original model. All right, so if you consider the concrete state of the original model with things like variable addresses, pointers that contain these variable addresses, and so on, it's clearly the case that these threads simply are not symmetric in the original program. They are not symmetric. They only become symmetric by doing the data abstraction. All right, and that things like addresses and pointers just go away. All right, that's certainly important here. I would certainly not expect this sort of reduction on the original models.
But in many cases, I mean, when predicate abstraction works, because you can blur these things. But in some cases, then it's harder, and then you have to refine, etc., and you realize that these abstractions were wrong. So now the symmetry, if you bring the symmetry there, I mean, I mean, the nice thing about your framework is that the model checking part is, you didn't discuss how the abstraction, the predicates are in, and the impact on the refinement, the process, the abstraction refinement. You make them orthogonal.
Right.
But I wonder if some cases, I mean,
well, the answer is,
what if you were titling more of these different
yeah, so the answer is
together?
probably the same as to why predicate abstraction works to begin with, okay? So predicate abstraction doesn't work everywhere, and I don't expect predicate abstraction to work in more places just because we have concurrency in there, okay? If anything, it will work in fewer places.
Or symmetry. You mean
The same thing with symmetry in this case, right? So, meaning predicate abstraction is only good for specific types of properties. And the same case holds here, so meaning the usual kind of control flow dominated properties. Yeah, that's the sort of stuff where I expect this to work very well. And I believe it's fair to say that for these sort of examples, these sort of properties, you also observe a lot of symmetry in the abstract model. Okay? So this works for specific types of properties, not for arbitrary data properties in particular.
So I have a question. I never thought of this counter abstraction as an instance of symmetry.
Right.
I still don't see what is the connection of symmetry with what you presented.
Counter abstraction is a specific instance of a symmetry reduction. All right? Namely one that takes care of this permutation symmetry, where you permute a vector of states. Yeah, so it's a specific instance of a symmetry reduction. There are obviously many other symmetry reductions, and counter abstraction is one of them.
I guess I always thought of only the kind of symmetry that Murphy does as symmetry reduction. Maybe
Yeah, so it's a different kind of symmetry reduction. All right. So one more thing to say about Murphy is that Murphy didn't work well on this. All right. So in fact, our experiments show that the counter abstraction works much better on this sort of workload than one that Murphy is doing. Okay. So this was obviously comparing two different kinds of symmetry reduction, but we wanted to see what happens if you compare this with a mature implementation of a symmetry reduction. All right.
Just if I may, sorry, but that for the comparison with the experimental comparison with Murphy,
yes,
it was not using, because Murphy is explicit, so it was not symbolic versus explicit.
No, it was explicit versus explicit, obviously.
Yes, so but you're basically specific encoding of
yes,
versus
so
there.
you can obviously make an explicit state version of all of this, right? Okay, so one more point I want to make, and maybe that could be the final point, is that so you cited that there's some bad history on using symmetry reductions in the case for software in some sense, especially symbolic representations. So one thing which we found a little bit odd is the following. So there haven't actually been that many reports of success using things like partial order reduction in a symbolic setting. Wouldn't you agree with it?
Not at all.
Right? And one thing we tried...
You don't need it in some sense.
Why is that?
Well, because of that work of partition-transition relation, for instance, in the 90s, which give you the same effect. Well, it doesn't reduce the state space, but it gives you a manageable, or so they claim,
right,
manageable state space representation, symbolic state space representation for asynchronous systems.
All right. So we found this discussion a little bit unsatisfactory. So we were a little bit disappointed that there's so little research on partial order reduction in a symbolic setting, right? So one thing we actually did is to try this. So this is a version of our tool that just implements partial order reduction. It's not obvious how you do partial order reduction in a symbolic setting, but it is actually doable. Like you read the paper, you get an idea how this is done symbolically, and you agree that this is how it's likely to be done. Okay, like all of these things, like the cycle condition, all these tests, you just need to implement. Okay, and this is what you get as a result. So one thing you do see that even though there's quite some blob here of fat black, there's also some numbers here. So one thing you could argue is that there isn't actually a clear winner here between partial order reduction and counter abstraction. Okay. By the way, partial order reduction against a plane exploration, even with this disjunctive partitioning, wins clearly. So there is a benefit of using partial order reduction. Okay, even in a symbolic setting. So I disagree with the statement that you've just made. Just from our experimental observations, the benefit is huge. It's not just a little bit. Okay. But one thing we did observe is that there's actually an even better story. So if you compare...
Sorry,
yes.
The quote was that it was this specific search technique
yes.
of abstraction partition refinement,
yes.
which is not the standard breadth first search type
right.
of combination. So that's,
yes.
so that's okay.
All right, so maybe this was a very specific... So in any case, we found partial order...
I do not know the detail, but
right.
that's...
So in any case, what we I think it's fair to say that this wasn't really looked into properly in a broader setting. I think there's very few papers on this at all, and very few people who ever implemented partial reduction in a symbolic model checker. Okay? It's certainly well understood for explicit state model checkers, and there's a lot of literature on this, hundreds of papers, right? But very few papers in the case of symbolic analysis. And one thing we did find is that it helps a lot, really. And as you see, we found it to have comparable performance with our counter abstraction. So what we then did is to implement a combination of our counter abstraction and partial OR reduction, with two actually combine. And this is something you do find in the literature. Normally you read the literature and you find the claim that symmetry plus partial OR reduction goes well together. Okay? And we found that to be true for the symbolic case as well. So if you take the partial OR reduction and the counter example abstraction, you get a tool that's yet another order of magnitude faster than just a plain counter abstraction itself. Okay? So and it's dramatically faster than just partial OR reduction by itself. All right? So the two go very, very well together. And it's not the case that one obsoletes the other. Okay, thank you. Oh, and one more question.
Did you try this on cache coherence protocols?
No, we didn't try this on cache coherence protocols.
A lot of this very similar stuff has been done on cache coherence protocols.
No, we didn't try this on cache coherence protocols at all.
Okay.
Why not?
I don't think we even thought about it.